Okay, can everyone hear me? Okay. Well, it's a great honor to be here at the Hot Topic session of QCrypt, and it's kind of exciting to cap off the week. It's been a really nice week of talks, and hopefully I can live up to the standard set. So one thing we have heard a lot about this week has been this notion of distributed entanglement, this idea that going forward, more than just QKD experiments, we hope to increasingly be able to establish entanglement between qubits that are very separated from each other in space. So for example, Jun-Sang Kim and the Monroe group have been working on this trapped ion setting. We've also seen, I think we had a presentation here from the Calgary people who are doing teleportation even over metropolitan fiber networks. And we hope in sort of the far future maybe to start working in a repeater setting where we can really do robust movement of entanglement across arbitrary distances. That's obviously kind of the dream. And my question, or the question I want to bring up, is now a question of application. What are we going to do with distributed entanglement once we have it? Once we can establish entangled qubits at a distance, what are you going to do with those entangled qubits? And what I'm going to talk about today is whether or not you can use it to improve metrology, whether or not you can use it to make some measurement better than you could without a quantum network, with just a classical network. And if you can, how? And if so, how much advantage does that actually give you? So just to explain a simpler case, first I want to talk about the case where there's no network. Kind of what quantum mechanics offers us metrologically in not a network setting at all. Suppose you want to measure some parameter, which we're going to label as theta, and you have n systems. You have n atoms that are sensitive to the parameter, let's say. And we'll couple that parameter theta into the Hamiltonian just like this. This is an external parameter, just a number, not an operator. And the question is, how well do you do when you scale this up to many, many systems, when you have a lot of qubits kind of acting as sensors? And we have what's called the standard quantum limit, which means that if you have no entanglement in the probe system, if your probe state is disentangled, a product state rather, you can get a scaling as 1 over the square root of n. And that just occurs because this is kind of the standard deviation of the mean. This is what happens when you make many measurements. It's kind of exactly equivalent to taking n measurements in a row with one system. But we know that if you have entanglement, you can reach what's called the Heisenberg limit, and you get this 1 over n scaling instead of 1 over square root n. And this is kind of believed to be the best scaling that's actually consistent with the uncertainty principle. If you think of this theta as being some energy splitting, you can imagine that you can only measure that energy splitting with kind of an accuracy 1 over the size of that energy splitting. So if you make the energy splitting n times bigger by entangling all these particles, you get that much enhancement. So this is what quantum mechanics does for us in a case where we only want to measure a single parameter. But now I'm going to shift slightly. I'm going to change one thing about this Hamiltonian, but it will make somewhat of a difference. I'm going to switch to an inhomogeneous measurement. And all I've done is I've taken that theta, which used to be an external parameter equally coupled to every qubit, and I've scattered it. There are now n thetas. There's a different theta coupled to every qubit. And the question becomes, what are we going to measure? What kind of measurements can we do on this Hamiltonian? And what kind of measurements would we like to do? So I'm going to make the argument that a simple case to look at for starters, and also a case that I can argue does have a lot of practical benefit, are these linear combinations. I want to measure this capital Q. This is going to be the new parameter of interest going forward in this talk. I want to measure this capital Q, which is some weighted sum over the individual theta i's. So these alphas are some weights on the thetas, and the quantity I want to measure can also be written as a dot product. If I want to write the alphas as a vector, and I can also write kind of the thetas as a vector of parameters that I want to learn something about. Just to justify this a little bit, you might say, well, why that? Why select this quite narrow range of functions? But this is actually, I would argue, a pretty interesting range of functions. You know, if I'm integrating a field against some other function, maybe to isolate off a spatial Fourier component or a particular spherical harmonic component, this is exactly what I want to do. I'd want to take some integral and I'd sort of sum over it and sample from it. And this is done in lots of different fields of science. For example, here I have some reconstructions of a brain from MRI scans that are done kind of order by order in spherical harmonics, and you can see as they add up, you slowly get a good picture of something that looks like a brain instead of a potato. Down here I have some images of the magnetic field of the moon, which was also kind of measured and reconstructed order by order in spherical harmonics. So these linear combinations are, in fact, kind of an interesting thing to worry about. Anyway, so as I said, we're going to be in a network setting. So I imagine that there is some network which is capable of quantum and classical communication. Here I've been very ambitious and I've drawn it across the entire world, but obviously we might imagine, especially if it's really is a neurology application or something like that, we're going to imagine maybe something smaller. But the point is that at every point in space, there is both a weight alpha, which we've picked. We've decided that we want to measure a particular set of alphas dotted into these thetas. And there's also some field, which could be a magnetic field or gravitational field. The basic idea is it's some external field that we can couple into the qubits of interest, or that just is naturally coupled into the qubits of interest. And as I said, we're going to assume this network is capable of quantum and classical communication. It can, for the purpose of this talk, I'm going to skip over the admittedly very hard problem of actually distributing that entanglement. We're going to assume the network is capable of creating whatever entangled state across its sites it wants to. And the question is, how can this measurement be done, and how much better will this network do with quantum communication than it would with classical communication? And so, just as in the other case, I kind of started from the standard quantum limit, and then I talked about the Heisenberg limit as a means of comparison, here I'm going to talk about a standard quantum limit for networks, which is perhaps kind of the setting of that network, but classical communication only, which means no entanglement between sites. Everyone's got their own qubit, they can make a measurement, and they can all call each other about it afterwards if they need to actually make the addition. So there's no entanglement between sites. The variance in this measurement, the square root of the standard deviation, is just going to be the weighted sum of the individual variances. This is kind of basic statistics. So I'm going to get something like this, just adding everything together in quadrature. And I'm going to go ahead and give everyone the best possible measurement, again, from uncertainty principle arguments. I'll assume that everyone can measure this delta theta I, everyone can measure their own personal theta I at some accuracy 1 over t. And so then it's quite clear, basic algebra, that what I'm going to get is some measurement that is proportional to the Euclidean norm of this alpha vector. So that this is kind of what's going to set the standards, and you can see that if you run through the arguments for what if I want to measure an average, you'll recover the standard quantum limit, not for networks, kind of, so to speak. But now I want to improve on this. This is the standard quantum limit, and if I was just here to present the standard quantum limit, I don't think they would have let me talk. So let's think about how can we do better given a quantum network. So I'm going to propose a very simple entangled protocol. That is a protocol that makes use of entanglement. And then we're going to just kind of worry about how much better does it do. So it's very simple. We start with the GHG state shared amongst all stations. And without loss of generality, I'm going to go ahead and set the largest weight to 1, just so that it's clear what the timescale is going to be. I can always do this simply by kind of changing the timescales. And then I'm going to evolve every qubit for an amount of time proportional to the weight. And what I mean by this is, what I've drawn here is kind of 3 timelines, and they're meant to represent the evolution of individual qubits in this scheme. So for example, this first qubit will evolve for an amount of time alpha 1t, and then I turn it off. The second qubit evolves for an amount of time alpha 2t, and then I turn it off. And the third one, I assume, is the one that's highest weighted, so it has weight 1 by assumption, and it evolves for the entire time, and then I'm going to make a measurement. If this kind of bothers you, if this shelving seems a little bit unnatural because it's not like you can actually turn off the external parameter, you can also imagine evolving forward in time, then applying an X operator at some point in time, and then you would evolve backwards. So if that's a slightly more complicated version, but it accomplishes the same thing. So now you need to make a measurement that actually tells you something about the quantity you're interested in. And you end up with a final state like so. You find that that phase there is exactly the Q you wanted to measure to start with. And then what you're going to do is every site will make a X basis measurement in the plus or minus basis. So the the observable I'm measuring is this product of local operators, which is nice. And you can run through the math very quickly, and you will find that this expectation value varies sinusoidally with frequency capital Q. And therefore, it follows that if you want to measure something with frequency capital Q, you can do so with an uncertainty 1 over t. And this already beats our standard quantum limit because it doesn't have the magnitude in it. And I want to make a couple other comments. First of all, the secure in the title, which I think is maybe not quite as strong a statement of security as often appears at QCrypt. But when I say secure, I simply mean that even if you learn any subset of these measurement results, because it's this parity measurement where we multiply all the results together, you don't actually learn anything about the observable Q unless you measure all of them, and you know all of them. So if n-1 of these measurement results are transmitted in the clear, and Eve hears all of them, she still doesn't learn anything about Q. And it actually turns out that this, even though it was this very simple, and as I said, it was kind of the most obvious, I think, protocol you could do, it's actually optimal in the sense of fish information, and that optimality is robust to arbitrary local control. You can do whatever you want to the qubits as long as you are doing something that doesn't depend on the parameters, and it turns out this is the best you can do. So let me just put up a comparison between this and what I called the standard quantum limit, or the disentangled case, or whatever you'd like to call it. So the idea here is that what we've removed is this factor of the magnitude of alpha. Component-wise, what that means is on the left, I'm just going to get 1. On the right, I get this sum in quadrature of all the weights. Remember, I assumed that the largest weight was 1, so the term on the right is definitely bigger than 1. And there are kind of two extremes here that I think are useful to look at to understand what we're extrapolating between. First of all, I could have an alpha such that only one element was 1 and every other element of alpha was 0. In this case, what I'm effectively measuring is the value of a single theta I, the value of the field at a single site. And in that case, both of these give the exact same answer, 1 over t, which makes perfect sense. If you only want to know a local parameter, having a bunch of entanglement thrown out all over the world will not help you at all. On the other hand, if you want to measure an average, you can plug in alpha equals 1 over n for every element of alpha, and you'll find that you recover the standard quantum limit for the disentangled case and the Heisenberg limit for the entangled case. So in those two cases, we're not really doing anything new here. What this does allow us to do, though, is exactly quantify what the advantage is in all these cases where, well, it's not that we only care about one site, and it's not that we care about all sites equally, but in all these in-between cases, we can now quantify exactly what the advantage is. I mentioned, and I kind of made a big deal about the fact that this was a very simple protocol, and it might not seem like it would be the optimal one, even though I've claimed it is, and in fact it is. And the reason why that is kind of interesting to explore. The reason it took us a long time to believe even that this was the optimal protocol, once we kind of formulated it, is that it seems like there's a lot of dead time in this protocol. Qubit 1 spends, what, 2/3 of this time not doing anything? Qubit 2 spends about 1/3. I mean, shouldn't you be able to use that time to make more measurement? It seems like you should be able to do something. And the question is this time all wasted? And I'm going to claim no, because the protocol is optimal. So how can it be optimal if it doesn't make full use of all these resources? And I think the easiest way to see why that is to present an alternative protocol, just on 2 qubits, and kind of explain what the issue is and why you can't automatically use that information. So we're going to start with this bell pair. And first we're going to evolve for the first weight, and we're going to accumulate phase on both qubits. Then I'm going to perform a disentangling operation. So I now have a product state again. One of the qubits has all the phase on it. Just by choosing which one is the target of the C0 correctly, I can do this. Then I evolve for the rest of the time, and I end up with Q on the second qubit, and then but I end up with some extra information over there, which seems to allow me to make some phase measurement on theta 1. So it seems like if I perform this protocol, which is more demanding than our other protocol, it required me to make a C0 measurement, or sorry, a C0 operation across the network. It required, so it did require a little bit more demands on the experimenters, but it seems like if I did this protocol, I would gain more information. And so this seems like a better candidate for the optimal protocol, at least, than my other one did. But the immediate problem is that it's actually not clear how you would leverage this. There's no a priori way to leverage that extra knowledge. And I'm going to demonstrate that by playing a game with everyone, hypothetically, because we don't actually have time for everyone to play the game. I'm going to think of the sum of 2 numbers, and you need to guess the sum. And I refuse to restrict the set of numbers. So this is clearly impossible for you to win with any finite probability, because I know a lot of numbers, and it will take you'll have a very hard time guessing which ones I'm thinking of. So I'm going to make it a little bit easier for you. I'm going to take a little bit of mercy, and I'm going to tell you one of the numbers. One of the numbers is 13. And now I challenge you to guess the sum I'm thinking of. And I think it's pretty clear to everyone that because, again, I refuse to give you any more than that, 13 is no luck for you. You will not be any better at guessing the sum once I reveal to you one of the numbers. So similarly, in the other protocol, even though I now gave you an extra measurement, which told you one of the components, you don't gain any knowledge about its sum with the other theta, because the other theta could be anything. And so knowing one component of the field better doesn't tell you anything about that combination. However, this is not quite true, because the only reason this applied is because I refused to give you any information about the parameters involved. In a real situation, you would know something about the set of numbers I was coming from. And so if I said these numbers between 0 and 15, by telling you one of them, I've kind of halved the amount of uncertainty. So in a real situation, where you have some prior information, for example, you're on Earth, you're measuring a magnetic field, you know that the magnetic field is going to fall within some certain range, simply because otherwise you would die. And that can be used to perhaps improve this. This only applies non-asymptotically, however. This is the real thing. I said we were optimal scaling of this with a number of measurements is. So although our protocol is optimal if you can make many, many, many measurements, for smaller numbers of measurements, it's possible that the other protocol I presented would actually be better. So, and the way you can think of that is if you do have asymptotically many measurements, you just make a few measurements until you sort of gain as much information as the guy who walked in with some prior knowledge. So kind of what's next for us, we would like to extend into the non-asymptotic region, which kind of requires moving to these Bayesian schemes that can incorporate prior knowledge. We'd like to work on what happens when there's noise on the system. Are there ways to calculate more complicated functions? As I said, I think that these linear combinations are interesting and important, but there are other functions out there. You may have heard of them. And continue developing maybe this applications. And we'd really like to talk to experimentalists, because it does seem to us that if you can do entanglement between two qubits and apply kind of diagonal disorder on them, you could take this measurement and you could tell us whether or not you're actually getting this kind of improvement. So with that, I'd just like to acknowledge my co-authors and my advisor, Alexi, and friends and money. So thank you.
Questions?
Very interesting talk.
Thank you.
So you mentioned.
I'm sorry, your mic is dropping
Yeah.
out.
You mentioned spatial networks of entanglement.
Right.
But it's much easier to send entanglement to yourself forward in time. Does that mean that if you have more, than one measurement, now the scaling, Heisenberg scale increases as 1/n rather than 1/n?
That's an interesting question. I hadn't considered. You're basically asking whether or not you can pull this trick with temporal entanglement. That's an interesting question. I haven't really considered it. It does seem to me that that would be possible. I don't see any reason it shouldn't be. I think I do want to stress, however, that it's not necessarily true that you get a 1/√n improvement in every case, because it only really all we can say is that it's 1/√n. 1/√n is the best case, but in general, you may do not as well if the integral over time you're talking about taking is different. Does that answer your question? Okay.
Any more questions? All right, so let's thank our speaker, and let's thank all of the speakers for these 2 sessions.